The places where stars and planets are born are among the galaxy's most beautiful locales. These cosmic landscapes change as new generations of stars light up and disperse their birth cloud. But the youngest stars seen here are already perhaps 1,000,000 years old. Hardly toddlers.
Stars and planets form in the dark, inside vast cold clouds of gas and dust, such as these pillars imaged by the Hubble Space Telescope.
The dust is so thick we can't see the infant stars inside, at least not with visible light.
With infrared light, Hubble can see through all but the thickest dust. Yet it's in those dense knots that the youngest stars are forming.
To peer inside them, astronomers need the James Webb Space Telescope.
With a mirror larger than Hubble's and performance optimized for the infrared, Webb will give astronomers their closest look yet at stellar birth.
We're flying through a computer model that represents astronomers' best ideas about the star formation process.
Reddish colors indicate thicker dust. The temperature, less than 400 degrees below 0 Fahrenheit.
Or less than 240 degrees below 0 Celsius.
That pinwheel ahead is a protostar, perhaps 10,000 years old. Protostars arise when a dense knot of dust, less than a light year across, collapses. But the details of the process are not well known.
Elsewhere in
Smaller, Earth-sized planets may take shape.
At least, that's what scientists think happens. It will take the Webb telescope's keen infrared eye to see what's really going on in the cold heart of stellar nurseries.
Over 20 years ago, the Astronomical League invited me to help participate in a new program called the National Young Astronomers Award. That award is made possible each year through the Astronomical League, and they choose really brilliant high school students who have done remarkable achievements in astronomy to receive this award. And today, Explore Scientific is the proud sponsor of these awards. This year, Julian Shapiro, who discovered an object called Shapiro 1, is with us. Kent Martz has him in our little remote studio at the 2024 Astronomical League Convention in Overland Park, Kansas. I'm going to turn him over, and thank you, Julian, for coming on board.
Thank you, Scott. I'm sitting here with Julian, and he just got through speaking, and his first public speaking about a discovery had Julian 16 years old, and it makes me giddy to just think about having an object named after you in space that you discovered. And it's Shapiro 1. It's a planetary nebula. He's also got other candidate planetary nebula and supernova remnants or something. They're studying them. And so it's possible by the time he's 17 or 18 years old, you're going to see Shapiro 1, 2, 3, 4, 5, 6, 7 out there. And it's just a fascinating, it literally makes me just giddy for him to have that. And it's at such a young age. So, Julian, tell us a little bit about yourself before how you got started in this and how you came at 16 to discover a planetary nebula that anyone could have discovered and how you did it. So,
Yeah.
so talk about that.
Okay, thank you. Yeah. So I got into astronomy when I was a kid here. About 6 or 7, I started watching a lot of space documentaries, and I moved out to the darker sky in North Carolina, and my parents bought me my first telescope, and it was an amazing experience to see the planets and a few deep sky objects for the first time, and that brought me into the world of astrophotography. And from there, I've been interested in astrophotography for the last 4 years, and I eventually wanted to try to find something new, a new target to photograph. So with my remote telescope now set up in Spain, I surveyed most of the constellation Cygnus, specifically in oxygen, to try to find new planetary nebulae and supernova remnant candidates. And I chose oxygen as a filter to survey in, particularly because it's not often imaged in, and it's really common in planetary nebulae and supernova remnant emissions.
And so you use a remote telescope and you had images, and so you just let computer processing, AI and smart technology find it, right? You just wait till the computer spit it out and said, oh, I found that, and now it has my name on it, right? That's how that worked, right?
Yeah, I looked, I with my own eyes, I looked through every single image.
Wait a minute, you didn't use AI to discover this? Or
No.
You used your Mark 1R and Mark 1L eyeball to do this.
Yeah,
Visually looking at every single object.
Yeah.
Okay. How long did it take you per night?
I spent about 6 hours per night, every clear night, imaging most of the time actually in oxygen and a shorter amount of time in hydrogen. And eventually I landed upon my first candidate, which was a small 35 arcsecond spherical oxygen blob. And upon looking a bit further into it, I confirmed that it was also present a bit fainter in hydrogen alpha. And I found central white dwarf in a binary system at the center.
And you jumped up and down and danced a jig and screamed for joy, or how did you contain yourself when you did it? Because you weren't certain, right? It was, you knew, but you didn't really know for certain. So what was that like?
It took a while to confirm. I first discovered it at the end of 2023, and it took many months of confirmation to get it finally released into my catalog.
Hey, Kent,
Yes, Scott.
have Julian bring his microphone closer.
Bring your microphone up a little bit.
Yeah.
Say something.
Hello?
Is that better, Scott?
Way better. Yeah, much
Okay.
better.
All right. So how did you get notified? Did the phone call, email, read it in a magazine? How'd you find out that Shapiro 1 was Shapiro 1?
Well, the first thing I did was I sent it to a friend who's also very interested in this area of planetary nebulae, and he was able to say that he was pretty certain that it was a planetary nebula. And so from that point, I emailed professor at Hong Kong. He's working with the Hong Kong University. They have the full catalog of planetary nebulae. And the moment I got back that email is when I knew that they had added it to my catalog. That was really that was most exciting.
I think most exciting is, for me, that wouldn't describe what it was like. I mean, I'm just grinning ear to ear for you because it's so cool. Okay, so you're done now. You discovered Shapiro 1. You're going to move on to fast cars and no, you're going to keep doing this?
Yeah. I've been surveying now in the Southern Hemisphere. I have multiple new planetary nebula candidates, as well as a couple new supernova remnant candidates. So those are still in the early phase, but I'm hoping to get those confirmed soon.
Okay, so we have your PowerPoint. Scott, can you cue that up and we go through that real quick?
Yes, I can.
This technology is amazing that, this isn't a telescope in your backyard. This is a remote observatory that you can schedule time on, or how's that work?
Well, this is my telescope set up there.
Okay, so
It's
you shipped it down there, or?
Yeah,
Okay.
it's a remote observatory set up on a pier that you can reserve.
Mhm.
There's a few of these services available, and I basically ask it every night to image a certain place in the sky using these narrowband filters.
So you let it observe. If it's clear weather, it's going to observe, download the data to a server. The next day, you're going to call the data up and look through it, or you look as it's dumping data in. Are you looking through it right then at night, or is this a daytime pursuit for you?
Usually I'm waiting until everything's collected and then stacking it all together.
Okay.
And then, spending however many hours processing the data and scanning through it for
Okay.
potential objects.
So, all right, so here we go. So just go through the slide, Scott.
Okay.
Is that it right there?
Yeah.
Okay, so the object is the blue thing down in the bottom left of his name. So what's this up here? It's on the top. It's another planetary nebula.
Yes, that one's called NEV2. It was discovered a couple decades ago.
Okay.
A few thousand times brighter. I had to dim it in this image.
Okay.
But it was known a long time ago.
So this is in the Cygnus region. Is this almost looks like part of the Veil Nebula? Is this part of the Veil Nebula? Do you know?
No,
Okay.
it's a emission gas in Cygnus. It's all hydrogen alpha,
Okay.
but it covers a large part of the constellation.
Okay. Next slide, Scott. So that's a picture of your telescope. What is it?
It's a 14-inch Newtonian.
Okay. On what mount?
Originally I had it on Paramount, and we just switched that to a GM.
Okay.
And it also has an ASI 6200 on there.
Okay.
With narrowband filters.
Okay. Probably a 5 filter wheel, 7 filter wheel,
We
like
actually
that?
just just upgraded.
9 filter wheel.
Yeah.
Okay, next slide, Scott. Okay, so let's talk about this slide a little bit.
Yeah, so these were photos I had taken previously. These are pretty common targets, Crab Nebula, Headphones Nebula. And this is what got me interested into finding a new one of these.
So these are all your pictures that we're gonna see?
Yeah.
Okay, all right. Go ahead, Scott.
Yeah.
What are we looking at here?
This was the survey area.
Okay,
So you can recognize the Tulip Nebula. You're there in the center.
right there.
Yeah.
Yep.
And it's an area with a lot of bright hydrogen emissions. That's been photographed many times, but there's not a lot of oxygen at this point. It's why I went to,
Well, you picked oxygen.
Yeah.
Because they ignore it.
yeah.
It gets ignored. Okay, so by doing that, you intentionally and through education increase your chances of finding something because you're looking in a way many other people, most other people haven't looked, right?
Yes.
Okay, all right, next slide, Scott.
Yeah, so these are the wavelengths that I've been photographing. Most significantly, oxygen 3, which is the second one there.
The green line in the
Yeah.
middle, right? So you have sulfur, double ionized sulfur, single ionized coming from the right, double ionized sulfur,
Hydrogen alpha,
triple ionized oxygen,
hydrogen beta.
hydrogen beta. Okay, all wavelengths of light. Okay. Next slide, please. Okay, so there they are right there.
Mhm.
And
Yeah.
so you can see yours again is the lower one of the two in the left-hand panel, and the supernova remnant is the blue light, correct?
Yes, that's a supernova candidate. It's a lot larger in size as well.
Okay,
About 40 arc minutes total, compared to the planetary nebula being only about 35 arc seconds.
and once again, when you saw it, you went back to the catalog and there was nothing there,
Yes,
just completely void there.
yes.
Okay, and what portion of Cygnus are we looking at right here?
The planetary nebula is on the east of Cygnus.
Okay.
So looking at the Tulip Nebula, it's right near there. If you go about a degree east of that, and the supernova remnant candidate is fairly close to Wolf-Rayet 134, which is a pretty popular astrophotography target.
So everybody's right there around it, and just didn't know what they were looking at.
Yeah.
That's the key to your success. Is that one, you were looking for something specific and you knew what you were looking at when you saw it.
Yeah.
Okay, all right, next slide, Scott. So life cycle of a star, is that what we're looking at
Yeah,
here?
just pointing out a couple of the key differences between planetary nebulae and supernovas. Planetary nebulae do leave behind a white dwarf, which is something we can identify
Right,
at the center of planetary nebulae, whereas supernova remnants, they have neutron stars and black holes, which we cannot detect in visible light. And supernova remnants also ionized sulfur in the surrounding interstellar medium, whereas planetary nebulae do not.
Okay,
Difference we can detect with sulfur.
so chemistry.
Yeah.
Effectively. All right, go on. Next slide, please. It's generating slowly.
Most of the is pretty dominant in oxygen, hydrogen,
Mhm.
just tiny bits of it at the edges, and you can see the background is very red from the Cygnus emission nebulae.
So almost like, looks like a little E almost,
Yeah,
or I don't know, little. I can see a figure hidden in there somewhere.
yeah, it has some interesting features. And this is largely, we think, because of the binary system.
Okay. Caused a disruption in the smooth creation of a nice evenly shaped
Yes,
shell. How old is this planetary
think-
nebula?
we think it's on the older size. We measured the distance of the planetary nebula, and from that, we measured the size of it, and we calculated it to be around 3.5 light years size.
Okay.
So,
And how far away?
about 19,500 light years plus the planet.
Yeah. Okay, next slide, Scott.
So on the top are survey images from DSS and the IFS H-alpha survey. And on the bottom left is the oxygen image, and on the bottom right is the hydrogen alpha image.
And you can match up stars
Yeah,
and see how it's completely invisible.
yeah. In these surveys, these broadband surveys, they were able to pick up nothing, and they moved through these panels very quickly. So not a lot of time was spent on them. And so this particular area in space was ignored.
Interesting. Because they're invisible in those top panels, but you can match up the stars and go, it's right there, but there's nothing there.
Yeah, after spending however many hours, I think 40 in each hydrogen alpha and oxygen, we were able to reveal it.
That's amazing. Okay, go on.
Yeah, this is the all-wise telescope, and the full all-wise survey image of the sky, which is actually the most useful survey that I found. And finding infrared signal helps confirm the nebula, which is on the next slide.
Okay, next slide.
So at the very center there, you can see near the yellow reticle, there's a bit of a red blob,
Mhm.
and that lines up with the size of the planetary nebula, and it's in the far infrared, which is what is emitted by planetary nebulae. And so we were able to use that to
Are you able to measure any redshift at all? Is there enough spectra from it to give you a redshift number, or is
it
it
would
not
be
possible?
it would be pretty minor.
Okay.
So it'd be hard to detect.
Okay. Next, Scott.
Yeah, so this is Sirius star system, Sirius A, the much smaller Sirius B, which is thousands of times fainter, if not more. And this was kind of the case that I ran into with my binary system, is that the main sequence star outshined the white dwarf, so we were not able to detect it initially.
So how did you detect it? Shorter exposure,
I
or
looked at-
just masking, or what?
I looked at the Pan-STARRS survey,
Mhm.
which is on the next slide.
Next slide, Scott.
And on the left there, you can see that's through the red channel, and on the right is in the blue channel. And we noticed, and I was looking through this, and I noticed there was an elongation in the blue channel. To the left there, you can see it's a bit more of an oval shape. And looking through the Gaia survey catalog, they actually marked that as a separate object to the main sequence star. So we were able to find that was most likely.
Are we talking about this area right here?
Look at the central star, the reticle.
There, okay,
Yeah, and go to the blue image. It's on the right.
okay.
You can see it's elongated on the left.
Oh, okay, yeah, I see that now. Okay,
Yeah, and it's
So-
just in the blue light, which is what.
which is the white dwarfs.
Yeah,
So we're looking at the star that's in the central reticle, the crosshair. And on the right-hand panel, which is the blue light, it's sort of elongated or squished a little bit. And that's the light coming from the very close dwarf. Are these companion stars, or are they just visual alignment?
well, we don't know for sure. It's very difficult to get a measurement on the white dwarf because it's completely outshined by this main sequence
Right.
star. But because of the morphology of the nebula, we think it's most likely a binary pair. because the feature is visible in the nebula
Okay.
itself.
Okay. So it's not just a visual pair. You think your supposition is your hypothesis at this moment, it's a binary pair.
Yes.
Okay. Moving on, Scott.
Yeah. So
Okay.
this is a comparison. On the left is image taken by John Hayes of known binary planetary nebula, and shows a lot of features there which you can look through. It has multiple shells as well as a halo and an outflow of gas. And I was able to match up that outflow of gas in my planetary nebula, which is quite clear on the bottom left, as well as
You can see the jet coming out of it.
yeah, as well as the potential halo on the western sides.
So this is building the evidentiary case is what you're doing.
Yeah.
It fits all the components necessary to be that.
Yeah,
Okay.
these planetary nebulae are quite similar, both in
They look very similar.
size and oxygen.
Okay. Going on, Scott. So now we're looking at the supernova remnant.
Yeah, so this is a much larger object, also visible in oxygen, and it's about, I think I mentioned this, 40 arc minutes
Right.
in size. But it's dominant in oxygen. There's a little bit of hydrogen, which I'll show in one of the next slides. But we have two very bright filaments, one on the west, one on the east,
Mhm.
then kind of a fainter, much fainter ring going around, which we need a lot more exposure time to
Yeah.
try to bring out.
Okay, Scott, go on.
Yeah, these were the initial discovery images. On the left, you can see the two west and east filaments. And on the right, you can see that east filament as well as kind of a connecting structure on the north. And more exposure time would later reveal that that was also visible in oxygen.
Okay, moving on, Scott.
Similar, this was the first color image that I made, those two, hydrogen alpha and oxygen.
Okay, and this is just a 2-channel exposure, right?
Yes.
Okay. Go on, Scott. Which one of these gives you more, I don't want to say pleasure, but more?
Mhm.
Well,
Yeah.
you know what I'm saying? Which one makes you go, oh, wow, I did, this is cool. They're both cool. They're both yours. Are they like different brother and sister? You love your kids the same, but they're different? Or does one do some more for you than the other one does?
Well, the planetary nebula was pretty clear from the start that it was most likely that, but the supernova remnant candidate is a lot more mysterious. We still don't know exactly what it is.
Okay.
So I think that gives me a bit more interest in researching it.
Yep. So what are we looking at here?
On the left is the sulfur image, on the right is the hydrogen alpha. We were not able to collect a ton of sulfur exposure yet, but near the center there,
That right almost in the dead center, there's a
Yeah.
little sort of an S swiggle right there.
Yeah, we were able to get
Right
a little
there.
bit of that filament. So hopefully with more exposure, we'll be able to bring out a bit more
Yeah.
sulfur.
Next slide, Scott.
Yeah, so on the left there is an image I took in collaboration with the Deep Sky Collective. The 525-hour exposure image of Cassiopeia A, and also collaboration with NASA Chandra X-ray to bring out some more of that, more of the outer shell. And it's a very clear circular young supernova remnant. It happened only around 1,000 years ago. And on the right is a comparison to this supernova remnant candidate, which is believed to be a much older object, many tens of thousands of years old.
So the one on the right is your candidate.
Yeah.
Okay.
So
Do you have a pet name for it? Like at first it almost looks like a Thor's helmet or something, but it's not clearly Thor's helmet. I guess do you get to pick the nicknames or
yeah.
just yeah, okay. All right, going on, Scott.
So this is zooming into a specific part of the candidate, and on the right there you can see that there's an outer oxygen shell, and then followed by an inner hydrogen shell, which is similar to supernova remnant that I compare this to, a much older supernova remnant than Cassiopeia A, most likely similar age to this object. And They show a lot of similarities here in terms of hydrogen, alpha, and oxygen structure.
Next slide, Scott. How many more slides are there, Julian?
There's only one.
Okay. Oh, okay. The question I was going to ask as soon as we got done with the PowerPoint, further research.
Yeah. So in the back there, you can see the SALT telescope. I was able to get a spectrum there recently on another one of my candidates, supernova remnant candidate in the southern hemisphere. And that's something I'd like to do with these two objects, as well as with my other planetary nebula candidates. Having a spectra is really the best way of identifying what an object is. You can see the specific emission lines going from left to right. The bright ones there are oxygen, hydrogen alpha. There's singly ionized oxygen there, small ones in between, and then nitrogen and sulfur. So comparing those allows you to get an understanding of the object. Specifically with sulfur, you're able to tell if it's supernova remnant or planetary nebula, etc.
Next slide, Scott.
So these are three other candidates I've been working on. On the left is maybe an ancient planetary nebula. We're still not sure. It's a very large oxygen structure. It has a bit more to the left of it. It's kind of almost an oval shape. That's the candidate I'm working on at the moment. The top right is planetary nebula candidate, quite similar actually to original one in Cygnus.
Shapiro 1.
Yeah, small in size, very bright in oxygen, slightly fainter in hydrogen. And in the bottom right, it's very faint, it's hard to see, is another supernova remnant candidate. Yeah,
Right there in the middle.
yeah, it's very faint. So
There's a center star almost in the middle.
yeah,
And it's just above that.
a
It's a galaxy. Let's say those are galaxies. We're looking at galaxies there, not stars, right?
What's interesting about it is that I actually got some new data on it recently. We're trying to believe that it might be related to galaxies as opposed to supernova remnant. So it's something that's
So
in the process.
it's a new structure of some sort that you're
Yeah,
figuring out what it is. Okay. Next slide, Scott.
should be.
That's it. Okay, so further research. So let's talk, obviously you're working in the Southern Hemisphere some, right?
Yeah.
And when you wrap this up, but spend a minute or so, talk about how your logic flow is and where you're gonna go from here. How do you plan your observing runs and bringing, because you're not just shotgun approach, you're being very targeted. How are those steps look like?
I try to look through specific areas in the Milky Way band. That's where a very large percentage of planetary nebulae supernova remnants are, that's where the large majority of stars are in a galaxy. So I try to pick areas that have not been imaged very deeply and survey those areas deeply, particularly in oxygen. And at the moment, I've been renting data on southern hemisphere telescopes. I don't have them down there. Well, through survey data, it's publicly available online, particularly in infrared, hydrogen alpha. And once I have a candidate, I'll search it up, just make sure it's not been discovered, hash database, and for planetary nebulae, look for that central white dwarf. From there, takes a few months of research and trying to get it confirmed, but that's the process.
So the process, wherever the universe takes you at this point. So obviously you're not gonna graduate high school and do nothing. Gonna go to college somewhere.
Yeah.
Have you been accepted to college anywhere yet? Have you applied?
No, not yet.
Okay.
I'm
I suspect you will have very little trouble getting accepted to some pretty good colleges.
Yeah. Well, I'm planning to major in astrophysics
Mhm.
as my biggest interest. I'm planning on going into kind of theoretical side, maybe a bit of observational astrophysics as well, but that general area is what I'm looking to study.
So, very cool.
Wow.
Very
Yeah.
cool. Wow, very cool. I don't know what to say. That's just, to see this from
Fantastic.
a 16.
Okay, so we do have some questions here.
Okay, some questions from the
Yeah.
audience.
It says,
Can you hear me?
what kind, David Derpat, okay, or Depat, watching on Facebook, he wants to know what kind of telescope did you use?
What kind of telescope did you use?
For this survey, it's a 14-inch Newtonian f3.3. I know someone who got this custom made a few years back. So,
Loaned it to you, bought it?
loaned it up first.
Yeah.
By
Now you're gonna buy it?
Yeah.
Okay. So it's how big was it?
14-inch aperture.
14 aperture at
F3.
3.3.
Yeah. So,
Okay. With and you said
Any
a
particular
VWO.
brand, I think that this person might be interested in the actual brand
What
of
brand?
telescope.
it's custom made. The
Custom made,
the
okay.
tube is from Orion Optics UK, and then the mirror was custom made and f3.3, which is not really a standard
Right.
focal ratio, but it's fairly similar to a lot of 14-inch f4 telescopes.
Okay. And you've got a ZWO.
6200 monochrome.
Okay, 1600 monochrome. And you shoot in monochrome because you have better pixel scale resolution, correct?
Yeah.
Whereas you shoot in color, the pixels there's more pixels, they're pulling color out of it, but that's not what you're after.
Yeah.
You're
and-
after data.
Yeah, and I'm after specific narrowband wavelengths, which
Mhm.
is ideal with a monochrome camera. So
Right.
you're capturing that hydrogen alpha and oxygen, triply ionized oxygen, in those monochrome.
And you're using every pixel, not every third pixel will pick
Yeah,
up
yeah,
the red, we'll say, or
Mhm.
the green or the blue.
Yeah.
So shooting in monochrome allows you to get a whole lot more detail, a whole lot faster.
Yeah.
Right? Okay. Scott, anything else?
That's all we have for right now, but I do have to say I am very impressed, and I think it's wonderful that someone of your age is doing this incredible work. It's you know, when you're in your youth and you find something like that, it's really, you've now found your life's calling, and that's there's a lot of young people who don't know what they're going to do, or have no idea. It's like they're just sort of lost out there. You're not one of them, okay? That's for sure.
Yeah.
And so congratulations.
Oh, and by the way, Scott, over his right shoulder
Yeah.
is the prize he gets. So both first and second place winners, and the first place winner is not here, so we can't interview them. But
Right.
Explore Scientific has donated the prizes for first and second place. It's an essential series, 127 millimeter Explore Scientific telescope with a couple of eyepieces and a finder scope, mounted on our Exos 2 GT PMC8 go-to system. So he's not going to have to schlep that back on an airplane with him. We're going to ship it to him so he doesn't have to take it back.
Good idea.
A great prize, and we hope you put it to use. It's yours. You can do whatever you want to with it. I'm just excited beyond belief that it just makes me giddy to think of Shapiro won, and you did that, and that's one of those things that there's 16-year-olds out there who
So
whatever, but you got some direction, and that's so cool.
I have a question. If you go to search for Shapiro 1 on the internet right now, it's not easy to find, okay? But just for our listeners, do you know the right ascension and declination coordinates of this object?
I haven't released the image yet, so that's why I don't know
Okay.
what to find, but it is cataloged online in the website called planetarinebulae.net. If you go to the catalog listing, go to Shapiro catalog, you can find all the details, including.
Okay.
The Shapiro catalog, that is
I love
fabulous. You'll live forever. Your name will live forever in astronomy. So go to
Planetarinebulae.net.
So spell
.net.
real quick.
Okay.
Spell solely.
So I'm going to add your objects to our PMC8 catalog.
Okay.
Okay.
All right.
And
So
so we'll put in the right RA and DEC, and if you want, you could also submit the images that you've taken and maybe some description, that would be very, very cool. So,
Yeah.
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 So it's Planetary, Planetary,
Yes.
NEBULAE
Yeah.
.net.
AE?
NEBULAE
Yes.
Okay,
.net.
I got that a little bit wrong. I will correct that right now. Planetary nebulae.
So what will it take for somebody to photograph the planetary nebula? I mean, somebody without a 14-inch custom-made F3 telescope, what are they gonna have to do?
It'll be a bit difficult, but I have a friend who shot it with their refractor, wide field refractor. Small, but the bigger challenge is that it's a bit faint. So you have to,
Data.
so just get particularly oxygen. So just get a lot of oxygen data.
So how many hours? 50, 60 hours, 8 hours, 3 hours? The more is always better in this situation.
Yeah.
But
Yeah. I'd say you should start to see it in at least in 10 hours, you should be able to see it faintly. And
Mhm.
then in 40 hours, you'll be able to see it very clearly.
okay. And again, it's 35 arc seconds across.
Yeah.
So it's pretty small. You're gonna have pretty good guiding to get it and not be fuzzy, but it's definitely doable, it sounds like.
Yeah.
That'll be cool. That'd be very cool. So congratulations on
Thank
what
you.
you've done. Absolutely phenomenal to see, somebody your age doing this in astronomy. And there's been multiple people, Scott, walked by and gave you a
Yeah.
thumbs up, and a couple have said, just keep doing astronomy,
Oh, yeah,
and
yeah.
it excites us old farts to no end to know there's somebody out there who still is fascinated by the heavens and has such a focus on where they want to go. So
Yeah.
very
We'd
cool.
like to invite him on to Global Star Party to give his presentation as well.
Yeah, so we can work on that, right?
Okay?
So you're now officially famous, at least in the world that we move in. You're a famous guy. All right, Scott, I think we're going to wrap it up.
Okay, all right. Well, thank you very much. Thank you.
Julian.
Thanks, Julian, and congratulations again.
Yeah. Thank you so much.
Awesome job. It's
Thank you.
really, it really is exciting to hear your story. Let me get it.